Wonderful. Okay. So today we're going to continue talking about uh, relational algebra and about um, more about queries. Today's we'll be hitting a more difficult type of query, I think. Um, Also, the homework has been posted. It will be due next Monday at midnight. Um, I'm trying to think. Yeah, I'll probably assign some other type of homework this week. Nothing written, but just some like some reading assignments. In particular, maybe some tutorials on using terminal and basic uh, bash commands. Let me ask first, is there anybody here who has experience with a terminal? Or, let me see, um, or who's done this, for example? SSH, is there anybody who knows what this means or um, has ever done this before? Nobody? Okay. So, yeah, for the next few weeks, I'll be trying to give you guys some readings and some resources to practice working on a terminal, basically. It's nothing hard, but it does take some practice. Um, a terminal is basically a program where you can type text to interact with a computer. Um, and you will use this uh, in order to connect to a computer located somewhere else physically. Um, SSH is for secure shell. A shell is like a terminal. It's just a text prompt, a way for you to type text and interact with the computer, give commands, run scripts, and also uh, uh, run a database client, so you can manage and query a database. Um, this database won't be on your computer, it will be on a remote computer. So, um, okay. But for today, we are still going to be focused on relational algebra. Um, let's see. Very good. Okay. Wait, no problem for this student. Yeah. Okay. I'll post the lecture. Please watch it and email me if you have any issues. Okay. Um, are there any questions about what we've covered so far with relational algebra queries? Do you want me to go back to any of them? No? Okay. Uh, let's see. Okay. Um, let's look at this query. Find the names of all people who frequent only restaurants serving at least one food that they eat. Um, let's see if this works. Frequents, eats, serves. Um, right. I think I might have gone over this after the previous class, but um, in any case, I want to take a different approach here. Um, so actually, and for the student I was going over this with before, this does not quite work. Um, these are people who visit at least one restaurant that serves something that they like. Actually, you know what? Well, let me move this down still. Um, let me go over the problem here. No, I don't know why it does that. Okay. So this was an attempt last class. I guess I'll put it here. Here we don't really need person. Okay. So there's a problem with this. And in order to show that, let's look at this example here. So what this is doing, again, for the query, we want people who frequent only restaurants serving at least one food that they eat. That is to say that there's some people who go to restaurants. They might frequent they frequent lots of restaurants. Some restaurants they frequent, even though they don't serve anything that they like to eat. I don't know. Maybe they meet friends there or something. Um, but there's people who will frequent restaurants serving things that they might not like to eat. Um, and we don't want those people, even if they also go to places that, or they also frequent places that they do like to eat. Here, we're interested in a more picky type of person who only goes to places that serve something that they like to eat. What this query here is doing, this one, this is going to return people who go to who frequent restaurants that serve at least one food that they eat, not people who only frequent restaurants that serve things that they like. Again, this is, I'll write it. This um, people who frequent at least Okay. So there's a difference between these two statements. People who frequent at least one restaurant serving at least one food that they eat, and people who frequent only restaurants serving at least one food that they eat. So they're similar. Wait, when do these relational algebraic expressions do we look to minimize memory spent? For example, should we try to do this problem with trying to take cross product of only two tables at a time rather than three? I would say do whatever works first. Make sure that whatever way comes naturally that is correct. Do that first. After that, you can think about how to make it more optimal. Yeah. And for this class, so long it's correct, that's fine. I don't know. Maybe I'll give bonus points or something if it's efficient on top of that. But correctness is the important thing for this class. Okay. So again, there's a distinction between these two queries, and this is a tricky query. I'm a little. I'm not exactly sure what the best way is to do this, because I don't just want to give the query and then explain it. Or maybe I should do that. No. Okay. Let me first explain why this is a little harder. Well, the reason why it's harder is because we want people who only have this property. I'm going to go off on a slight tangent, and then we'll come back to this. I will copy this query though. Oh, let me see. Well, it's fine. I'm in the wrong notebook, but whatever. Okay. Here. Something called quantitative reasoning. Okay. Okay. So this is, I'll also try to provide a reading for this called, I think, this is by another professor in the business school. Something like basic reasoning or something. It's like, it's a very nice packet. It's like 10 pages or something, 10, 15 pages that talks about basic logic. I'll put that on the course website. One of the things that it talks about, though, is this idea of quantitative reasoning. So that is, there's something called a predicate. This is a definition. I don't know why that's happening. Predicate. Okay, so I'll be using this word quite a bit, a predicate. A predicate is just a statement that is either true or false. We've already seen predicates before. For example, the select statement. When you do a select and then you want, food equal to food two. This here is an example of a predicate. It's something that's either true or false. And this is applied to a statement, or in this case, a record. And it can have many parts, clauses, connected with ands or ors, and this kind of thing. Okay. Um, um, okay. So these here in yellow are just notation for each of these. The and the or I've already used before. For a not, I'll just write kind of a little right angle. These are operators, so you can take two predicates and connect them together using ands, ors, and nots. And then you can create a larger predicate that way. Quantifiers are there's only two, and that is for all and there exists. There's other ways of saying these, although they're the same. Let's see, for all, let's see, for each, for every, okay, so formally in quantitative reasoning, there's two symbols. This upside down capital A, which means for all, like a capital A for all, and then a backwards capital E that stands for there exists. Logically, these are two sides of the same coin, although when we're speaking, we might use other words. Like if there's at least one, then that means that there exists something. If there's at least one of something, then that means that there exists one. For all, we might say each. For each of these, it's true. For every one of them, it's true. For all of them, it's true. I'll try to use more of for all and there exists, but for example, in this query here in the bottom, you'll see here's at least and only. That's right. only. So here, the reason why I'm bringing these things up is for you to be able to look at a sentence in English and try to play around with it, rephrasing it using logic, to try to rephrase it in a way that's going to make it easy to write a query for. Okay. So the way that this is written now is kind of very straightforward, plain English. Um, uh, no, I'll get to rephrasing that in a minute. Um, but just so you know, this is sort of where I'm going with this. So here, this only, this that's really saying that that's a for all statement, and here this is a there exists statement. So find the names of the people. Where for all of the restaurants that they go, there exists some food that they eat that is served there. Um, okay, fine. Oh, another. No, we'll save that. Okay. Oh, okay. Um, and I went over this kind of quickly before, but um, is there anybody who doesn't know what this is? What I just drew? You can message me privately or whatever. This is a truth table. Um, But if you've never seen it or you don't know how it works, you let me know. But I think all of you have taken some type of class where you might have seen this before. Is there anybody who has not seen this? Can I please explain? Okay. So this is called a truth table. Here, a zero is going to correspond to false, and a one is going to correspond to true. Everything here is about things being either true or false. There's no in betweens. Everything in this world is either true or false. So instead of writing true and false again and again, or a T and an F, I'm going to use ones and zeros just for the ease of notation. So let's say that I'll make a variable x1. I'll say x1 is today is Monday, and x2 let's see, I don't know, whatever. It's sunny. Okay. So here I have two variables, two Boolean variables that can either be true or false. Now they could both be false. One of them could be false and one of them could be true. Or both of them could be true. So this first line here is it's false that it's Monday. So it's not Monday and it's not sunny. I don't know. Go for afternoon walk. Okay, so let's say that if it's Monday and it's sunny, then you will go for an afternoon walk. Here, if it's 0, not Monday, and it's 0, not sunny, well, then I'm not going to go for a walk. I'm only going for a walk if it's Monday and if it's sunny. So if it's just sunny, I'm not going to go on a walk. If it's just Monday, like in this third line, I'm not going to go on a walk. But in the fourth line, if it is Monday and it's sunny, then I will go for a walk. So this is called a truth table. You have variables here that you can assign truth values. You write all of the different combinations of truth values. That will be some power of 2. Here, there's 4 possibilities, right? Because you have 2 variables, each of which you have 2 choices for. So if it's Monday, that can be true or false. If it's sunny, that can be true or false. So altogether, you have 4 things. If you had 3 choices, you'd have 8 combinations and whatever. And is only true when everything is true. Or, on the other hand, like this, x1 or x2. Now I'll go for, I don't know, let's see. If it's Sunday or if it's Monday, I don't know, take a nap. So if it's a sunny day or if it's a Monday, I'll take a nap. So here on this first line again, if it's not Monday and it's not sunny, well then is it sunny or Monday? No. So then this is also false. Is it Monday here? Is it Monday or sunny? Yes, it's sunny. So that's true. Here, is it Monday or sunny? Yes, it's Monday. So that's true. And obviously for this last one, that's also true. So this is the truth values for the AND function. This is it for the OR function. And for the not function, that's easy. Not x1. You just flip them, flip the bits. Similarly for not x2. So for example, here's x2. And so not x2 is this column. Here, if this is a 0, if that's false, then not 0 is a 1, like this. Okay, so that's a truth table. Great. Okay, and that's the and, or, and not. Great. Okay. I need to talk about two more things. Oh, by the way, are there any questions about that before I move on? About the truth tables, or how they work? Go back up. Okay, I'll ask somebody to help me construct one in a minute. Uh, First, does anybody know what De Morgan's law is? This would be something you might have run into in a programming class again. Afreen, can you unmute yourself?
Hello.
Hey, yes, very good. So you say that De Morgan's law is a rule for evaluating logical expressions. Can you give me an example?
Um, I remember learning about it in Foundations of Programming. I
Mm-hmm.
think there's a rule for if you have like in parentheses, if you had like X and something and then and X or something like that, you would there's a rule for how you would go about that, but I forgot exactly what the rule is.
Okay. Good. Yeah. So this is how to distribute a knot uh, in an or and clause. So actually, where is this? Afreen, if you're still there, maybe you remember here. If I say A and B, okay, now I'm going to make that a clause, and I'm going to say, now I'm going to not it. So not the expression A and B. Do you know what this would evaluate to?
Yeah, I think it would be um not A or not B.
Very good. Yeah. So when you're okay, and just for the sake of completeness, how about this one?
So that's not A or B, right? So that would be
Mm-hmm.
not A and not B.
Very good. Okay. Right. So what De Morgan's law uh, is it's about when you have this knot, how do you distribute it? Well, it's pretty easy when you're distributing it to a variable, right? Like here. Whoa. Okay. Um, yeah. Not applied to an A becomes not A. The notable thing is that for the operators, it has the effect of swapping them. So an or becomes an and becomes an or. Right? Um, okay. Boy, that might make a good exercise. I'll leave this as an exercise for you. You can construct a truth table and show that this is true. Um, uh, I'll get you kind of started. Um, well, here, already above, you can call this A. You can call this B. Here we already have A and B, right? Let me erase this. And I can compute then not A and B, which is just taking this column and then flipping all the bits, right? Okay, so now that's not the quantity A and B. And then here we can say not A, here's not B. And then here, if you do not A or not B, we'll just go through it. So if we take both of these and we OR them together, 1 or 1 is 1 here, 1 or 0 is 1 here, 0 or 1 is 1, 0 or 0 is 0, and lo and behold, we notice that here, yep, I don't know why this is doing that. Yeah. You'll notice this column and this column are identical. So this is the proof for that one. You can prove the other one in a similar fashion. Okay, so De Morgan's law, that's a good one to know. If you have a logical statement and then you apply a not, you can distribute the not all throughout the statement. Any true-false part of that, it will just be flipped. Like not A, or the not applied to an A will just be not A. And then any ands become ors become ands. Okay? So that is a very useful thing to know for the way that we'll be manipulating some of these queries. The other thing is very obvious. I don't really even want to call it a trick, but note A is equal to not A. Okay? If you take something and you negate it twice, you just get back the original thing. So if the statement A is today is Monday, taking the double not of that would be saying that, for example, it's not true that today is not Monday, which is a very long-winded way of saying that today is Monday. It is not true that today is not Monday. It is saying that today is Monday. Okay, so it's an obvious thing, but fine. Okay. This is the complement of A. Okay? That's called the complement. Just the negation. It's also called the complement. Okay, so all of this is to try to give you some tools to be able to rephrase queries in particular ways. Now, there is a problem with this. How to say? there's a problem with the way that this is phrased and the way that database management systems process queries. Recall. DBMS evaluates a relation one line at a time. The system has no memory. Besides the one line or entry, record, whatever. Okay. So the way the database management systems are built is this way, that they read things one line at a time, and it looks at it like this, right? It doesn't look at multiple entries of the table. It looks at one entry, makes a decision about that entry, and then it moves to the next entry. And after it's made its decision is final. It doesn't remember after it moves on to the next line. It doesn't remember anything about the line just above it. It cannot change its mind and go back or revisit something again. It goes line by line, top to bottom, down one time, and that's it. So it evaluates things, looking at this record, and then after that, looking at this record, make a decision. For example, the select, right? Are we going to keep this or are we going to delete it? You can't, the view of that isn't multiple rows, looking here and maybe here. No. You get to look at one line, and that's it. Make your decision and move on. Okay? That's the way that these systems work. Now, that is why this kind of throws a wrench into things. Let's say that here there's, I don't know, John, I don't know, McDonald's, fries, John, McDonald's fries, hold on. John fries. Okay, whatever. Let's say it's something like this, right? Like where there's an entry like this. Maybe this is name. This is name 2, food 2, food restaurant. So maybe, what I'm thinking is like this comes from foods that a restaurant serves. This comes from foods that John eats. And fine, I'll just go and do this. Name Restaurant 2, McDonald's, John. Okay. If you have an entry like this, where this is like a frequency, that's coming from the frequency table. This part is coming from a serves table, and then this part is coming from a eats table. Okay, so we've cross-multiplied these three tables together, and now here's John at McDonald's. McDonald's serves fries, and John eats fries. Do we keep this row or not? Again, the problem here is with this only. Here, we can tell that John, from this one line, we can tell that John goes to at least one restaurant that serves something that he likes, but we don't know if it's the only restaurant that he goes to. That's the problem with this phrasing. And any way you try in a straightforward way to, like here, using this type of pattern where you cross-multiply things, select and project, this is not going to work. You can take as much time as you like trying to come up with this type of structure, and it's not going to work well for you. The reason why is because of this only word. So, the way that this needs to be resolved is to, instead of beginning with a for all, to begin with a there exists. Because here, looking at one line, you can say this exists or not. As soon as you find it one time, then you know that it exists and you're good. For all is different. For all, in some sense, you need to have kind of like a memory, right? It's true for the thing that I'm looking at. What about all of the rest? Like, I can't, if it's true for this one that I'm looking at, and then I put it down, well, now I've forgotten it. And if I look at another one, I've forgotten if this is true or not. So you're not able to work with for all statements, but there exists works fine with somebody with no memory, because if they're looking for something, like in, I don't know, here's a gigantic bag of black balls, somebody's saying that there exists a red one. Well, I can reach in the bag, look at a ball and ask, is it red? And if it's not, throw it out. And I don't need to remember about that one. All that I mean, if it were red, then I would have stopped. So you can just keep going in and you can look, and is it red? No. Is it red? No. Is it red? No. And if you find a red one, you can stop immediately and say, yes, this one's red. And that's the way that your queries need to be phrased. So if you see words like only, if you see words like for every, for all, for each, at the beginning of a query, that should be a hint that you might need to rephrase the query in order to make it easier. Or in order to phrase it correctly so that the database system understands it. For us, human beings, it might sound monotonous or long-winded. In this same way, right? If I say that today's Monday, I could also say that it's not true that today's not Monday. I get the same point across. And it'll be similar to that. We'll rephrase this query. Oh, let me go back really quick. Yeah, so we're going to rephrase this query and change the for all to a there exists. So De Morgan's law shows how you distribute a not on truth variables and operations. Quantifiers is something different, and it's pretty easy. I'll just write it, I think. No. Okay. That's another note about the negation of quantifiers. So not for all is the same thing as saying that there exists. If I don't know, if a teacher says that not all students passed the test, that's the same as saying there exists a student who did not pass the test. Similarly, if there does not exist a student who failed the test, then that means that all students passed the test. If there doesn't exist one who failed, then all of them succeeded. Okay? Great. So those are kind of straightforward, but necessary. And now here's what we're going to do. You might already see it. We're going to take this expression and we're going to not the entire thing. We're going to negate the entire thing twice. Okay? So we're going to, right now, this is A, okay? And what we're going to do is to take the not of this. So we're going to do this. So we're going to not this whole thing twice. The reason why we're doing this is because of this for all. This only is messing things up. Okay? It has to be, you have to make the query of the kind where you can go line by line and make a decision exactly once, looking at only that one line and nothing else. You cannot do that with for all or only, as I tried to show here. But if there exists is fine. So, the high-level view, we're going to find the names of all people. This takes a little bit of work and practice. And the point of this is for me to try to have it so that you can derive yourself the query. Okay? This class, I'm walking very slowly through this. And I'll leave you at the end of class with another one to work on. Okay. Now, we're taking this query, find the names of all people who frequent only restaurants serving at least one food that they like, and I'm going to negate it one time. So, find the names of all people who frequent. Okay. So this part isn't going to change. By the way, this all is not like this all, right? Return all the names is not, that's just return the names. Some words get overloaded here, and you just have to kind of think a little bit about um, if it's a quantifier like this, um, or another part of speech, even though it's the same word. Okay. Um, okay. So this part, uh, frequent. Okay. So applying this negation, this first one here, find the names of all people who, where there exists a restaurant they frequent, serving, here I'll say only foods they don't eat. Okay, so this whole thing, this is it's a strategy of considering the complement. It's my own word. I don't know what to call it. How do I make this make a little bit more sense? Okay. Let me finish this up first. So this first negation applied to the sentence would make the query find the names of all people where there exists a restaurant that they frequent that serves only things that they don't eat. The second negation is going to be everybody except those. Okay, that's what this does. This is now this one is going to be a set difference. I.e., all people except. Right? So, the rephrased query, find the names of all people who frequent only restaurants serving at least one food that they eat, is going to be find the names of all people except those people who frequent a restaurant that serves only things that they don't eat. Those two are equivalent. The second one, if I can go back here, now I'll write the query and go through it. Okay. Okay. Hold on. There we go. Like I said, it's a harder looking query. Okay. Why? And now, if you try to look in the book, or maybe if you can find any resource that does a better job, or approaches it differently, let me know. Um, I just think it's super annoying. I don't know how it's expected that people are supposed to come up with queries like this. But this is the query, and the justification for how to get there is what I'm trying to offer. Where is this coming from? What's even going on? If we look at it bit by bit, let me pick this one. This part is saying return all people except. So remember, here, let me give myself some more room. Okay, here. So what we're doing is we're taking all of the people and we're going to remove these, the unwanteds. Okay? So instead of finding the people that meet our criteria, we're going to come up with the people who are the opposite of that, like the antimatter. You know, like matter as antimatter that's like exactly the same in every way except for certain properties. And then if they meet, like they annihilate, like they're exact opposites of each other. So that's what the complement is. Instead of finding the people that meet our criteria, we're going to take the people, find out who their opposites are, and then we're going to take everybody and then remove the opposites. And then what will remain are the people that we want. Okay, that's the way that this is working. So the first part of this query is all of the people, and now we're going to remove the opposites. So here, what is this doing? This are finding restaurants that serve foods that people eat. Um, okay, so we're getting the names here of people and restaurants where the people, those restaurants serve a food that those people eat. But from the frequents table, now, we're subtracting those people. So these are people who frequent only restaurants serving nothing they eat. Okay? So, for people who frequent only restaurants serving nothing that they eat, wait, I'm sorry, people who frequent restaurants serving nothing that they eat. I don't know if that's an only. Those are people who frequent. I don't think that's an only. Actually, people who frequent restaurants serving nothing that they eat. Yes. No. People who frequent at least one restaurant serving nothing that they eat. Okay. So if you have people who frequent restaurants serving at least, or people who go to restaurants including at least one that serves nothing that they eat, and you remove them from the population, then what you're left with are people who only go to restaurants serving at least one thing that they like to eat. Okay. I'm going to start talking myself in circles. But what I didn't want to do is to just give you this query and say it works. Like you have to, I believe you, there should be a way to derive these things. I mean, there has to be. I mean, somebody came up with them in the first place. This is the best way that I can come up with for doing it. There's certain queries that after some practice, it'll sort of jump out at you. But overall, what this is doing is, I'm calling it considering the complement. But really, it's just, there's two ways of achieving the same result. Depending on the query, one way, you might have to use one way or the other. Now we've seen both. This way is taking everything and then removing the unwanteds from the population and then returning what remains. The other way, for all of the previous examples that we've seen, is more like you have a collection of things and then you're picking it up, and then if you like it, you're adding it to the results. So you're picking out the good ones from the population, and then you're returning the good ones. This is different, where you're taking the whole populations and removing the bad ones, and then you return what remains. Okay? That's the difference between the same result, right? If there's black balls and white balls and you want only the white balls, you can pick out the white balls one by one and then return the white balls, or you can go and pick out all the black balls, and what you're left over with is a bag of white balls. Now, the reason why we had to go through it this way is, again, because this word only appears earlier in the query. Too early. Too early meaning that, here, we already know, here's a for all, here's a there exists. If we negate it, we're going to be changing this. And if this were a for exists and that a for all, then we're okay. This is the more straightforward way of writing the query. In fact, let's look at a previous query here. Find the names of females who eat both yogurt and salad. Let's see, does that one work? Nah, one doesn't really work. Okay, whatever. Fine. Okay, because we're coming up to the end of class, I want to pause and see if there's any questions about this. Actually, I'm not going to give you another problem because there's more in your homework to practice with. There will be one more like this. I'll go over on Thursday for more practice. But yeah, for today, this query or anything that I talked about. Any questions about any of that? I don't like silent classes. I mean, with this many students, there's got to be somebody who's lost or has something to say. No? Okay. Well, then I'll quickly review this again. Hold on. I have a question about the last question of my homework, but I can wait until people just want to clarify my understanding of it. Okay. Sure. Great. Well, I guess that's it. Yeah, if you guys don't have any more questions, I mean, this is what I wanted to get through today, especially this quantitative reasoning stuff, and why we're doing this. When will the homework be posted? The homework's already posted. I will be posting the recording for this lecture, yes. Okay, well, I guess, yeah, you guys can log off early if you want. For the student who has a question about the homework, yeah, feel free to ask. Let me stop the recording here.